Okay, welcome to lecture here. We're going to continue on chapter 3. Get everybody in. Okay, so we're going to continue on talking about bonding like we've been doing here. So last time we started talking about bonding and two types of bonding. We have ionic bonding. And as we talked about with ionic bonding, that is when we have bonding between a metal and a non-metal. And in an ionic bond, what essentially happens is the metal will lose electrons and the non-metal will gain electrons. The metal then becomes positively charged or a cation. The non-metal that picks up the electrons become negatively charged or an anion. And what holds that together is, again, no sharing of electrons here. It is the electrostatic attraction between a positive and negative charge that holds that together. Absolutely, again, no sharing of electrons. And that is different than what we saw here and sort of finished up with last time, which was covalent bonding. And covalent bonding is between two nonmetals, and different than really when we get a metal and a nonmetal together, because the two nonmetals are essentially very close to each other on the periodic table. They share very similar sort of properties, and some of those properties they share that are very similar is the fact that they both really want to hold on to their electrons. They both really want to actually gain electrons. So what happens when two nonmetals get together is the best that they sort of could come up with, sort of a livable situation, is that they will end up actually sharing electrons. And that's what's known as a covalent bond. And that's what we see here on our screen between the two fluorines, which obviously are two nonmetals. Since they are the same element, they will actually share the electrons between them and make a bond between them, and that's what's referred to as a bonding electrons. We also show in our sort of Lewis structures here the dots, which are the non-bonding electrons, are the lone pairs, and those are electrons that are not involved in bonding. And again, that's very different than an ionic bond, where we take a metal, which is kind of on the opposite side of the periodic table, and the non-metal, which on the other side of the periodic table. And in the case of metal and non-metal in an ionic bond, metals have all the sort of properties that they want to get rid of their electrons, while the nonmetals have all the properties to gain electrons. So that's why when a metal and nonmetal get together, we do have that transfer of electrons that occurs. And that's also why when we get two nonmetals together, we have the sharing of electrons that's going to occur. As we'll be talking about here, the sharing of electrons may be equal and may be unequal sharing of electrons, but any type of sharing of electrons is essentially what's classified as a covalent bond. And we'll talk about the different types here as we go through. So a Lewis structure does represent really covalent bonding. Again, remember sort of a Lewis dot symbol or an electron dot symbol is the symbol and one valence electron for each, one dot for each of the valence electrons that are present. The number of valence electrons can be easily found by looking at the periodic table, and the group number is the same as the number of valence electrons. So everybody in group 1 will have one valence electron, everybody in group 2 will have 2, and so forth along the way. So the whole goal of bonding, as we also talked about last time, pretty much the whole goal of bonding is for everybody to end up at the same electron configuration as a noble gas. And for metals and nonmetals, they will transfer electrons to do that, where the metal will go backwards and basically end up with the same electron configuration as the noble gas before it. Nonmetals will gain electrons, go forward, and be the same noble gas. Now, on our non-metal, the way they're able to achieve really kind of the same electron configuration as the noble gases is through sharing of electrons, which means for the most part, everybody will get to 8 electrons, except for hydrogen, as we also talked about, I think, a little bit. Hydrogen, again, only needs 2 electrons, because if you look at the periodic table, just after hydrogen is helium, which is number 2, and that's a noble gas. So hydrogen only needs 2 electrons, basically to get to that noble gas configuration. So again, here we see something like water, for example, and if we look at water, just like we kind of look at the F2 that we saw previously, by sharing electrons, the oxygen here will share with two different hydrogens, and by sharing those, what they ends up doing, as we can see on the bottom right there, is the oxygen is able to, through sharing of electrons, get to that 8 electrons that it needs, while each of the hydrogens here again get to 2 electrons. And as I just talked about, that's enough to get hydrogen to helium's configuration and be happy. And again, the oxygen there is able to gain those electrons and get basically to neon's configuration, essentially, or a noble gas configuration. Same thing here through what we saw earlier last time, the sharing of those electrons between the two fluorines, again, allowing each of the fluorines in that bond to reach 8 valence electrons and be happy again. They have essentially reached that noble gas configuration. And that, again, is really the whole point of all bonding, is for that effect to happen. Everybody wants to be just like the noble gases, and that's because noble gases are very stable. So they're very stable, they're chemically inert, and that's sort of the purpose of it. So obviously 8 seems to be a big theme in bonding, and it is, and 8 is what is sometimes referred to as the octet rule, an octet meaning 8, and basically what it means is when atoms come together and start forming bonds, they will continue to form bonds until pretty much everybody has 8 valence electrons around them. That is, again, the goal. And the before is that gets them to the noble gas configuration. The one exception that we'll come across in this class is hydrogen. As I talked about earlier, again, hydrogen should only have 2, and that is all it needs to get to helium. So when you draw hydrogen in pictures, it should always be on the outside and essentially look like this. As I might have drew last time, you should never be putting dots around it because that is wrong. Never double bond to hydrogen because that's wrong, and definitely never triple bond to hydrogen because that's wrong. Pretty much that is what hydrogen should look like in any sort of picture that you draw. If you use the line to represent the bonding electrons, or again, the 2 dots to represent the bonding electrons, but again, should never have any dots around it, should never make a double bond or triple bond. And that's what's sometimes referred to as the duet rule. Duet obviously meaning 2. So again, hydrogen just needs to go forward 1 spot on the periodic table to reach that helium configuration. Any questions on that? So that rule is obviously very important in terms of bonding. You want to keep that in mind as we start talking a little bit more about this. So let's just talk a little bit about different types of bonds and multiple bonds. So there are single bonds, which we've sort of been talking about, and a single bond is when a pair of electrons are being shared. And again, you could represent it as you see in this picture with the dots, which is perfectly fine for our bonding electrons. Or again, in lieu of the dots, you can use 1 line. Every line represents a pair of electrons. So here we have 1 line, which is a single bond, and that represents 2 electrons. When we go to something like CO2, we have some double bonds happening. And by double bonding, which is necessary for CO2, it is necessary so that they can get to 8 electrons. So in this case, the carbon actually has to double bond on both sides, gets it 4 electrons there and 4 electrons there, which gets carbon to 8. And each of the oxygens have 2, 4, 6, and 8 electrons happening as well. So in certain cases, in order to get somebody to the octet rule, sometimes a double bond is necessary. And as you can see here, sometimes 2 double bonds are necessary to that 8 electron. So in a double bond, that is 2 lines, which represents 2 pairs of electrons, or a grand total of 4 electrons in that particular case. And then we also have triple bonds that are sometimes necessary in order really to meet that octet rule. And here's a couple of examples. The triple bonds are nitrogen here. By making that triple bond in the middle, gives each of the nitrogen 8 electrons on each side, and that helps it meet the octet rule. In the case of the carbon here, each of the carbons by triple bonding to each other now has 8 electrons there and the other carbon also has 8 electrons. And still our hydrogen, as we talked about before, only has 2 electrons in each of these cases. And again, able to make everybody really happy. So a triple bond, 3 lines are 3 pairs of electrons, grand total of 6 electrons. As I mentioned before, for me, I usually do use lines to represent bonding electrons, but if you don't, you can obviously use dots if you'd like to. Yeah, so if your question is, if you're just asked to write the electron dot symbol for oxygen, for example, you would just draw it kind of with its appropriate number of dots, which would be 6 in that case. So that's just your question of if I was asked to draw the Lewis dot symbol or electron dot symbol, you would look something like that if that's what it is. When it hooks up in a sort of Lewis structure and stuff like that, again, it will be sharing some electrons with some other atom, and it will obviously get to that 8 electrons around it. If your question is either form is fine in terms of you could use lines or dots, if that's your question, then the answer is yes. And that's for bonding electrons. So those are the electrons that are involved in a bond. So you can use the line to represent that, or you could use the dots. So technically, if you drew the Lewis structure for this, you could draw it kind of either way is perfectly fine. I personally, and a lot of people, usually a lot of times use the lines to represent the bonding electrons, but you don't have to necessarily. Other questions? Okay. So how do we know if these electrons are going to be shared equally or unequally in a bond, especially a covalent bond? And what really helps us sort of determine that is what is known as electronegativity. And electronegativity really helps us decide, you know, are these electrons going to be shared equally? As we'll see in a later slide, the definition of electronegativity is the ability of an atom to bring electrons towards itself. So if something has really high electronegativity, it means it really wants to bring electrons and basically grab electrons and bring them towards itself. And on the periodic table, as we will see as well, just to kind of preview it, it increases as you go this way and decreases as you go down on the periodic table, with our good friend fluorine being the most electronegative atom that you could have. So in terms of the differences in terms of how those electrons are shared, it does depend on the 2 atoms involved in the bond. So if we had something like H2, because they're both hydrogen, we would expect the electrons to be attracted to that hydrogen and sort of the electrons to be attracted to the hydrogen on the left to be relatively equal. So they're going to be equally kind of pulled in each direction. And we would expect that the electrons would stay in about the same location, not really going one way or the other in that type of bond. And this type of bond where we really do get what is referred to as equal sharing of the electrons, that is what is sometimes referred to as a nonpolar bond, or sometimes referred to as a nonpolar covalent bond, because it is sharing electrons. Most people just go with the nonpolar bond, leave the covalent out of it, but it technically is a nonpolar covalent bond. So if you have something where you have equal sharing of electrons, that is what is referred to as a nonpolar bond. And what that essentially means is that bond is, for lack of a better description, neutral. There's no negative side, no positive side. It's that really perfect kind of equal sharing of electrons that occurs when you get perfect equal sharing of electrons, like you would in H2 or F2. That is also what is sometimes referred to as a polar covalent bond. I'm sorry, as a pure covalent bond. In terms of what happens when we actually do switch it around and switch out, say, one of those hydrogens for a fluorine. Now, looking at between hydrogen and fluorine, these are 2 different elements. And as I just mentioned, fluorine is actually the most electronegative atom you could have. So what's going to happen in this case is all those electrons are going to be really attracted to the fluorine side and not so much going to be hanging out over here on the hydrogen side. And what that's essentially going to do is create a situation where more electrons are hanging out by the fluorine, and that's going to make it partially negative, while the hydrogen will become partially positive. Those are what I refer to as delta symbols. So delta positive, delta negative are partially positive or partially negative type charges. And that's because the electrons are hanging out over here. And obviously, if the electrons are hanging out more on the fluorine side, it's going to be more negative than the hydrogen side, which would be less negative and more positive because those electrons are moving away. Another very common way this is represented is with an arrow. This is what is sometimes referred to as a dipole arrow. And it always points to the side that's more electronegative. And this side that kind of makes a plus sign, it's a sign that's more positive. So it always points to the side that's more negative, the sign that kind of makes the plus sign on the back there to the side that it's more positive, and that's the way you could do this. Now, in this case, unlike H2, where we had equal sharing of electrons, and that's a nonpolar bond, or as I was trying to say there when I muffled it there, a pure covalent bond. This here, when we have unequal sharing of electrons, is what is known as a polar bond. So a polar bond, or is really a polar covalent bond, is unequal sharing of those electrons. The result of that is what you see on the screen. In that bond, it creates a side that's more positive, and it creates a side that is more negative in that bond, and it gets a separation of charge. Why do we say that this is only partially positive and partially negative? We say that because they are still sharing electrons. Even though they're not equally sharing electrons, there's still some aspect of electrons being shared between the hydrogen and the fluorine. And that is different when we talk about a sodium ion and a chloride ion coming together. Here, there is no sharing of electrons. There's been a transfer completely of electrons. And that's why the sodium actually has a +1 charge and the chlorine has a -1 charge, because that electron is completely transferred from one side to the next. In a covalent bond, because there's still aspects of sharing, it's only partially negative on one side and partially positive on the other side. Any questions on that there? Here's probably a better picture of what I was drawing there. So if that kind of pink is the smear there, we can see there's much more electron density hanging out, near the fluorine than it is the hydrogen. And again, that's going to cause this side to be more negative, this side of the bond to be more positive. Get that right. And again, this is what is referred to as a polar bond. I'm not sure about CaF2. That is an ionic bond, yes. So that's what we were talking about last time. And calcium fluoride, the case of calcium, it's got its 2 electrons, right? So when we get our nonmetal and metal together, the electrons will transfer here. And again, this is why when we look at something like calcium fluoride versus what we're talking about here, because there's been a complete transfer of these electrons from the calcium to the fluorine, each of the fluorines end up with a full negative charge. The calcium ends up with a full positive charge. And again, it's that attraction that holds those guys together. And that's what makes an ionic bond, which is very different than what we're talking about here. Again, the electrons are moving this way, but they have not completely transferred. So they're still hanging on to the hydrogen and the fluorine. It's just that they're unequally being shared, and it does become partially negative on one side and partially positive on another side. So when we sort of think about the different types of bonding, like the 3 types of bonding that we talked about, you could kind of think of it as this sort of situation. On one end of the extreme, we have really an ionic bond, like something like, say, barium bromide. And in this case, the barium, same deal, going to completely transfer its electrons over to the bromine. And in this case, needs 2 of them to do so. And that's going to give us our cation which is positively charged, and our anion, which is negatively charged. And again, no sharing of electrons here. While on the other end of the stream, we have a nonpolar covalent bond, and that is between two nonmetals. And here we have sharing of electrons, which holds that together. And it's actually equal sharing of electrons. An example would be like the H2 that we saw, the F2 that we saw. Again, equal sharing of electrons between that. And again, just to remind, this is a metal and a non-metal together here. And sort of in between those two is a polar bond, or a polar covalent bond. And that also is two nonmetals that happen. Also sharing of electrons. The difference is this is unequal sharing of electrons. And that's something like HF, where again, more electronegative on the fluorine. HBr, if you like, you know, something like that. OH, for example, or electronegative that way. These are all examples of polar covalent bonds. Everybody here is still sharing of electrons. They're just not sharing them equally. Over here in our nonpolar, they are technically equally sharing the electrons. And on the other end of the stream, metal, non-metal, absolutely no sharing of electrons. A complete transfer of electrons from our metal to our nonmetals. And again, that's why in a polar bond, as I was mentioning, we don't get a full negative charge or a full positive charge, but we get these partially positive and partially negative charges because they are still sharing, but it's not being shared equally. So basically all the electrons are vacationing closer to the fluorine, for example, going to make that side more negative, while all the hydrogen there, all the electrons are moving away from it, going to make it more positive. But they haven't moved in such a way that they have completely jumped to the other side, and that electrons have completely transferred in that particular case. And that's sort of the three different types of bonding that we've been talking about. Any questions on that there? Okay, that's essentially what it says underneath all my bad scribble there, is basically what I just drew on the slide there. So what helps us decide if we're going to be sharing equally or unequally? And it really is the electronegativity. And as I mentioned before, the electronegativity is the ability of an atom basically to bring electrons towards itself. The higher the electronegativity, the greater they want to bring electrons towards itself. And that's why when we look at the periodic table, and that trend increases as we go this way and decreases down. And if you think about this part of the periodic table, that is where all of our nonmetals are. And that's why our nonmetals typically gain electrons and become negatively charged. While if you think about this side of the periodic table, that's pretty much where all of our metals are located. And that's why they typically give up their electrons really easily, because they have really low ionization energy. Ionization energy is the energy needed to remove an electron. Electron affinity is, I like electrons, so it has low electron affinity, high ionization energy, and that's why metals typically will lose electrons. Nonmetals are opposite. They have very high ionization energy, which means it takes a lot of energy to remove an electron, so it doesn't really happen a lot. But they have very high electron affinity, which means they're very happy to take an electron on and gain an electron. And that's an extra O here. Fluorine has high electron affinity and high ionization energy. And again, it will basically attract those electrons towards itself, while sodium has the opposite there. It's not looking to attract electrons, and it's really not looking to hang on to its electrons all that much. So that's why it helps us see metals making those positive guys. There is actually a way you can sort of figure it out, and Linus Pauling came up with a method to do that, and it's an electronegativity values that run from 0 to 4, 4 being the most electronegative, 0 being not so much. So what you could do is basically take the two elements that are involved in the bond, and you could subtract their electronegativity difference. And if you have a difference in electronegativity, which is what delta En means, difference in electronegativity values, and it's anywhere from 0 to 0.4, that difference, it's considered a nonpolar bond. If your difference in electronegativity is above 0.4 to below 2, it is some type of polar bond. And if typically your difference is above 2, it is some type of ionic bond. Not perfect on 100% of the time, but these are the general sort of cutoffs that are used to help you decide if something is polar, nonpolar, or ionic. I'll be honest with you, for ionic, you don't even need these values. As soon as you see it's a metal and a non-metal, put ionic. That's pretty much what it's going to be. It's a safe bet. But really, electronegativity values will help us out a lot with covalent bonding and determining whether or not these things will be shared equally or unequally. And here's sort of a table of that. There's a more fuller table of that. And again, you could kind of see some things here. So for example, if we take our couple of examples we had, if we take our good friends sodium and chlorine, if we look up sodium's value for electronegativity, it is 0.9. If we look up chlorine's value, it is 3. And basically, what we would do here is take the difference. So larger number minus smaller number. So difference in electronegativity would be 3 minus 0.9. That gives us a difference of 2.1 in terms of the electronegativity. And if we look back, which I think will answer your question as well, if we look back at our cutoffs here, anything above 2 is an ionic bond, which is what we would expect. Anything from basically 0.5 to 2 is a polar bond, and anything from 0 to 0.4 is nonpolar. This would be a table that would be provided for you if you needed it. So this is the table of electronegativity values, and it would be provided for you. You do not. So I think that answered both questions. I think they'll pop up. So you will be provided this table. You should know the cutoffs probably, yes. So that 0 to 0.4 being nonpolar, 0.5 to less than 2, polar, and above 2 be ionic. So if we look at something like we had like F2, for example, that F would have a value of 4. This guy would have a value of 4, which means when we take the difference, that is 4 minus 4, that would be 0. And this would be definitely a nonpolar bond. This would be also classified really as a pure covalent bond. That's like perfect equal sharing of electrons happening there. If we look at our HF, for example, that we also saw, H is 2.1, F is 4. So if we take the difference there, that is 4 minus 2.1, that is 1.9 as the difference. And that is, as we see here, right below 2. So it is definitely still a polar bond. It is also very close to like those electrons are going to jump ship, but they're not. They're still hanging on and is considered a polar bond. So why don't you try some? How about the carbon-hydrogen bond? How about the nitrogen-oxygen bond? And how about sulfur and oxygen? And one last one, why don't you determine, we'll do nitrogen and chlorine. So those 4, take a second, use electronegativity and determine, is the bond polar, nonpolar, or ionic? Okay, let's take a look and see. So we'll start with the carbon and hydrogen. So carbon is 2.5, hydrogen is 2.1. So if we take 2.5 minus 2.1 for the difference, that is 0.4. 0.4 is pretty much the cutoff for nonpolar, and this bond is considered nonpolar. This is also why that cutoff is there, because carbon and hydrogen is pretty much the only bond or the major bond that you find in an organic compounds. And organic compounds are nonpolar, so that's really almost why the difference is there. If we look at nitrogen and oxygen, nitrogen is 3, oxygen is 3.5, so 3 and 3.5. So when we do the nitrogen oxygen, that is 3.5 minus 3, gives us 0.5. 0.5 is above 0.4, so this would be a polar bond in this case. If we look at sulfur, which is 2.5, and we look at oxygen, which is 3.5, the difference there would be a difference of 1. When you take 3.5 minus 2.5, that definitely is above 0.5, but below 2. So this guy as well would be a polar bond. In addition, up here we have nitrogen, which has a value of 3. Chlorine has a value of 3. So if we take the difference in electronegativity, that is going to give us a difference of 0. And this bond would also be a nonpolar bond or a covalent bond. First off, any questions on how to do the calculation there to figure it out? And like I said, obviously, if you need this table, it would be provided for you. Yeah, so usually you just take the larger number minus the smaller number, so you get a positive number. That's usually the way you do it. So the positive and negative doesn't really matter here. It's actually the difference in the numbers, the important part. So always just take the larger number minus the smaller number, and you have to worry about it. Let's talk about a couple of things here. First off, you sometimes don't even need the table. So as I mentioned before, if you have a metal and a non-metal, you don't need the table to tell you it's going to be ionic. So definitely you don't need it. Secondly, if you have two things that are in the same period, so for example, our nitrogen and oxygen. Here's our nitrogen, here's our oxygen. If I didn't have the table, I know that oxygen is further to the right. And remember, as you go up and to the right on the periodic table, it's a pretty safe bet that oxygen would be more electronegative than nitrogen because they're in the same row or period. Now, if we look at sulfur and oxygen, these guys are actually in the same group. And we see that oxygen is further up than sulfur. So without even the numbers, you can make a pretty safe bet that oxygen should be more electronegative than sulfur and make that assumption that we are going to have a polar bond. So sometimes you don't even really need the numbers. You could just use the general trend to figure it out. This may also throw you, you're like, hey, this is two different elements, but they got a non-polar type of situation. And that relationship is what is sometimes referred to as the diagonal relationship. And actually, let me just flop to the next one. And if you look at the relationship on the periodic table, nitrogen is here and chlorine is here. Nitrogen is further up on the periodic table, but chlorine is further to the right. That is what is referred to as a diagonal relationship. They cancel each other out. And that happens in a couple places. Carbon and sulfur also diagonal of each other. One is higher up, one is further to the right. So they end up canceling out their effects. So sometimes it is possible to have two elements that are different and still will share the electrons equally. And usually non-metal, again, that diagonal sort of relationship, it sometimes comes about. But for the most part, probably 9 times out of 10, if it's two different elements, probably going to be unequal sharing of electrons. Again, there is the occasion where it could be the same. But definitely, if you have the same element, it's going to be nonpolar. So you don't need the table for those guys. Always going to be nonpolar. The last thing is when you think about the electronegativity difference, say between carbon and hydrogen, that was 0.4 difference. If you look at something between carbon and sulfur, the difference is 0. these are both considered nonpolar bonds. And as I've been kind of saying earlier, when you do have a difference here, this is, again, some people will call it a pure covalent bond when you have that difference. It is still technically a nonpolar bond, but sometimes people will call it a pure covalent bond to imply that you got that perfect equal sharing of electrons. In the case of carbon and hydrogen, is considered nonpolar and equal sharing of electrons. In reality, though, there's a slight unequalness that's happening, right? They're slightly going towards carbon, but not to an extent that people consider it unequal sharing of electrons. So it's not perfect equal sharing when we got something like 0.4 difference, but it's enough that it's still considered overall to be equally shared. So again, we want to use electronegativity values to help us determine if a bond between two atoms, are those electrons going to be shared equally or unequally? And that's really the only thing that will tell us, is simply that is between these two atoms, are those guys going to be sharing those electrons equally or unequally? And that's what we use our differences in electronegativity values to help us determine that. Question on that. So as I mentioned, the reason we do get that transfer of electrons in an ionic bond is because if you just think about the location of those guys, they're on very different sides of the periodic table, metals and nonmetals, and they have very different electronegativities. So like I said, metals are pretty much take my electrons, nonmetals are like thanks, picks them up, and they want to take them, and we get that full transfer of electrons. But again, when we do get to our non-metal interaction with covalent guys, as you can see, everybody's pretty much clustered here on this side of the periodic table, which means they share very similar electronegativities. So the best that they could do is some sort of sharing. And again, that may be equal sharing, maybe unequal sharing, but some sort of sharing occurs there. All right, and there's from your book, the cutoffs that we were just talking about as well. So if you want to reference it, you can. Again, it doesn't work 100% of the time. There is some differences there, doesn't necessarily work, but those are the general cutoffs that most people use in terms of that. All right, so let's talk about actually how to draw Lewis structures properly. And you do want to follow sort of these rules I'm going to talk about here. And if you follow these rules, you should end up with a pretty good structure in terms of a Lewis structure. If you decide just to sort of do a piecework, which means you draw every individual guy by itself and try to figure out how they come together, you probably will end up with a picture with too many electrons, not enough electrons, too many bonds, all those type of things. So the first thing you want to figure out is when you're drawing a Lewis structure for a covalent compound, you want to figure out what is the logical arrangement of everybody together in terms of how all the atoms basically fit together. To help you decide that, usually the center atom is occupied by the least electronegative atom. So usually the least electronegative atom is in the center. And for the most part, everybody else is probably attached to it in most cases. Hydrogen is never found in the center because hydrogen can only have 2 electrons. So if it's in the center, it's going to have more than 2 electrons. And fluorine, which is the most electronegative atom, will never be in the center because it's not the least, obviously. So fluorine and hydrogen never in the center, and least electronegative usually is in the middle. Now, the most important thing really is the second one here. You want to count up the total number of valence electrons available to you. And that's from the periodic table. You want to count up the total number of electrons. And if something does have a charge, so if it has a negative charge, it means it gained electrons, and you need to add that to your total or you'll be short. And if something has a negative charge, we want to subtract. So that should be positive charge here. Sorry. So anything that has a positive charge, we want to subtract that positive charge from the total. Again, positive charge means that it lost electrons in that particular case. The reason that number is important is because when your picture is done, you should have exactly that number, no more, no less electrons. You got to hit it right on the nose. Now, the next thing you want to do is once you have the arrangement, you got the total number of electrons, you want to make a single bond from the center atom to each of the outside atoms. I personally use lines, so you want to make one line from the center guy to each of the outside ones. You want to figure out how many electrons that is, subtract it from your total. You will then have some electrons left over. Those electrons go on the outside atoms in pairs as dots, so dots, until all the outside atoms have 8 electrons, except for hydrogen, that should only have 2. Once you put up all the electrons on the outside, and if you still have electrons to go, then you go to the center atom and put dots on them. At that point, you probably should have put up all your electrons in your picture. If you didn't, probably something's wrong, perhaps. At that point, what you want to do is make sure everybody has met the octet rule. That means everybody has 8 electrons around it. The exception is hydrogen, that should only have 2. If somebody does not meet the octet rule, that is when you want to double bond, and you want to try to double bond to fix that problem. And if a double bond doesn't work, what you want to do next is triple bond. So you want to save double bonding and triple bonding to fix something. Very common, people want to just double bond and triple bond right out of the gate. I'm just going to lay up some lines on everything because it just looks prettier probably when I put all those lines in there. And you will end up probably with the wrong picture. So I highly recommend you wait, you double bond and triple bond if necessary to fix a problem, not create a problem like it usually does. That is a lot of words, so let's go through it and actually see how we go through these steps together. So let's take a look at NF3, and if we want to draw the Lewis structure for NF3, one of the first things you want to do is figure out the total number of electrons. So we'll start with the group number for nitrogen, which is 5. That means nitrogen has 5 valence electrons. There are 3 fluorines, and fluorine is group number 7, which means it has 7 valence electrons. That is like 26 valence electrons, if I'm not mistaken there. So that number is really important because when my picture is done, I need to hit that number on the nose. I got to be exactly at 26. Logical arrangement here, I have 1 nitrogen and 3 fluorines. Nitrogen's probably in the middle. Fluorine is around. Also, fluorine is the most electronegative, so it cannot be in the middle. I put the fluorine here on the bottom. You could put the fluorine up on top. It doesn't matter, so you could draw it either way. I put this fluorine here on the bottom. Again, you could put it on the top. It works the same. All right, now that I have the logical arrangement, now that I got my proper number of electrons, I'm going to start with 1 single bond from the center guy to each of the outside guys. Remember that each of those lines represent 2 electrons. So I just used 2, 4, 6 electrons here. And if I subtract that off, I still have 20 more electrons to put on this picture. Those electrons go on the outside atoms until each of the outside atoms have 8 electrons, and they go on in pairs. So this would be 2, this would be 4, this would be 6. That one is full. This now would be 8. This now would be 10. This would be 12. That one is full. 14, I think, comes next. 16 and 18 electrons I just put on. And if I count up my electrons, I now still have 2 electrons to put on my picture. All these guys on the outside have 8, so they're full. So now I go to the center atom, and they go on in pairs. And that's my last 2, gives me 0 left. If I look at my picture, I've now placed 26 electrons. So that is 1, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26 electrons. I want to make sure everybody has 8 electrons around it. And in this case, everybody has 8. Each of the fluorines are the same. So that is 2 right there. I'll just darken it. That is 4. That is 6. And that is 8. So all the fluorines are exactly the same. They all have 8 electrons around it. And our guy in the middle there also has 8 if we count it up here. Maybe I could get there. Again, this is 2. This is 4, this is 6, and now this is 8 for our nitrogen. So all the fluorines have 8, nitrogen has 8. That would be the correct Lewis structure there. Again, all single bonded, no double bonds happening there. Question on those steps. So why don't you try this one? Why don't you try H2S and see what you come up with? Draw the Lewis structure for that one. Okay, so let's take a look here. So again, we want to start with the total number of valence electrons from the periodic table. Hydrogen has one valence electron, and there are two of them. And remember, the group number equals the number of valence electrons. So sulfur is group number 6, so it would have 6 valence electrons. So that is 8 valence electrons that our picture should have here. And in this case, we would put the sulfur in the middle, hydrogen on the outside because it cannot go on the inside. We're going to follow the same approach. We're going to make one single bond from the center to the outside. That is 4 electrons. That leaves me 4 more to go. I'm going to fill those on the outside first, but I cannot put any more on the hydrogen as it has 2 in its field. The other hydrogen on the left there is also filled. That means I still have those 4 electrons. So then we need to go to the center atom, and they do go on in pairs. So that is 2, and that is 4. And that would give me, if we look, 8 total electrons have been put up there. The hydrogen has 2 electrons. Hydrogen on the left has 2 electrons. Sulfur has the 2 electrons on the right with the hydrogen, 2 electrons on the left with the hydrogen, which is 4, and 2 up on top, which is 6, and 2 on the bottom there, which would be 8. So sulfur has 8 electrons, makes it happy. Each hydrogen has 2 electrons, which is all it needs, and it's happy. Again, no dots on the hydrogen. Question on that? Okay, why don't you try another one here? I think you have. Actually, let's not do this one. Let's do NO3 minus. Let's see what you come up with. Okay, let's take a look at this one. A little bit slightly different. We got a couple of things going on here. So we want to follow the same approach. So nitrogen is group number 5 on the periodic table. There are 3 oxygens, each is group 6, and we do have a negative charge here for this polyatomic ion. Negative means that it gained electrons, so we do need to add 1 to the total, otherwise you're going to be off. And again, that negative means that it gained electrons. So that is 18, 19, 24 valence electrons here. Logical arrangement would be nitrogen in the center, as it's the least electronegative here. Oxygen's on the outside. And again, if you look on the periodic table, oxygen further to the right than nitrogen in the same row, which tells you it is going to be more electronegative. We're going to do 1 single bond to everybody here. That is 2, 4, and 6 electrons. That leaves me some more there. I'm going to go with some bad math and go with 18, hopefully. Those are going to go on the outside ones first. So we're going to go 2, 4, 6, 8, 10, 12, 14, 16, and that is going to be 18 at that point. That takes me to 0 here. I have now placed all 24 electrons here, and we want to make sure that everybody is good. All the oxygens have 8, so 2, 4, 6, and again, if I just kind of highlight it here, 8 electrons. They are all identical, so they all have 8. The problem, though, is our nitrogen. Nitrogen has only 2, 4, and 6 electrons, so it is short. So this is not good. So we do need to fix it. So one idea might be, hey, let's just put those. A couple of electrons there, and if you thought that, well, the problem with that is it now has 26 electrons, and that is too many. So you cannot just lay up a couple more electrons there and hope for the best, because you will end up with too many electrons. So we do need to make a double bond in this case. And this is the part where we want to try to first make a double bond to fix this problem. All of these oxygens are identical to each other, so you can make the double bond anywhere you like. I'm going to make the double bond on the top one, so I'm going to make the double bond right here. Now, you may also say to yourself, if I do that, I am still at 26 electrons, so that's not good. And the oxygen on top now has 2, 4, 6, 8, 10 electrons, and that is definitely not good either. So when we do make a double bond, in order for us not to end up with too many electrons, what we're essentially going to do is take a pair of electrons and we're going to bring them in to do that. So what I'm going to do is I'm going to take a pair of electrons from that top oxygen. I'm going to take these pair of electrons and I'm going to bring them in to make that double bond. And when I do that, I will end up with a nitrogen that has a double bond to the oxygen. By bringing those electrons in, also erase the electrons up on top, I now end up with this guy on the side that looks this, and this guy over here, which looks the same. And usually we put a little bracket around it and a minus to make it look pretty. But if we look at everything, everybody now has 8 electrons. Nitrogen with the double bond, that's 4. Single bond to the right and left, 6 and 8. Double bonded oxygen, 2 and 4 for the non-bonding electrons, and 2 and 4 for the 2 bonding electron pairs, and that's 8. And each of these single guys are 8 as well. You could have made the double bond, like I said, to the guy to the right. It would look exactly the same, except that this guy would remain single bonded. This guy would become double bonded, and this guy would also become single bonded or remain single bonded. And these two structures are exactly the same. They are what are known as resonance structures of each other. Resonance structures are essentially 2 structures or more that you could draw that represents the same thing. And in this case, since we could have bonded to the right, we could have done that. We could actually draw one more resonance structure where we bonded to the left oxygen. And it would have looked like this. All 3 of these guys are what are referred to as resonance structures of each other. And the truth is those double bonded electrons are delocalized, which means at any given point, they may be up on the top oxygen, but then they may go to the other oxygen, may go to the other side, to the other oxygen. The real one is pretty much somewhere between all three of these structures. You would only need to draw one of these structures if it didn't ask you to draw a resonance structure, which you probably won't be asked to draw. That's exactly right. If you had a positive charge, you would need to subtract that from your total. I'm going to say outside of our class, to your question, you want to probably stick for our class. This is probably the logical sort of arrangement for everybody. One guy in the middle, some other guys attached to it. There's some other things that would help you decide if that's a better structure than one of these. And you probably would find out that this one here that we drew is actually the better structure than what you sort of proposed in there. So there are different ways you can technically hook up things. And there's something known as formal charge, which we don't talk about in this class. And formal charge is something that can help you decide, you know, what structure might be better. So for other reasons, probably this structure would be the right one here. And for our class, it's usually pretty straightforward, center guy and things attached to the center guy. So to answer your question on the other one here, for example, why don't you draw this one here, NH4 plus, and see what happens. So why don't you draw that guy, and that might answer your question about the positive charge. See what you come up with. And heck, while you're at it, why don't you draw SO2 as well? It would not matter. So much like the previous one, in that arrangement of the nitrogen in the center, oxygen to the left, oxygen to the right, you could put the oxygen on the bottom in the picture or the oxygen on top. Either way is fine. Most people just draw with oxygen up on top, you know, because it kind of looks right, I guess, rather than note down. It kind of looks upside down, but technically it doesn't matter. You could draw it either way. It would be. So on that one, that is absolutely correct. So nitrogen is 5. There's 4 hydrogens each at 1. And again, the plus here would be -1 in that particular case. Okay, so let's take a look and see how we're doing. So we did get our total here. So that's 5 plus 4, which is 9. And again, because of the positive charge, we need to subtract 1. So we will get 8. And logical arrangement, nitrogen in the middle, hydrogen's got to be around because it cannot be in the middle. And again, one single bond to everybody. That is now 2, 4, 6, 8 electrons, and that's it. So we have 2 electrons for all the hydrogens. Nitrogen has 8 electrons. Again, because it's something with a charge, a little brackets and a little charge up there to make it look all nice. Let's take a look at the next one. Sulfur is group 6, and we have 2 oxygens, which also happens to be group 6. And that's going to give us 18 valence electrons when we look at it. Again, looking at sulfur and oxygen, they are in the same group. So it looks like this. So even if you weren't sure in terms of electronegativity, oxygen is further up, which means it should be more electronegative. That means sulfur should be in the middle. Oxygen should be on the outsides. Going to follow the same approach, one bond, single bond to everybody. That is 4 electrons used. That's 14 more to go. That's going to go on the outside ones in pairs. So that is 2. That is 4. That is 6. That one is full. That is 8, 10, and 12. That one is full. At this point, I have now put 16 electrons on there. I got 2 more to go. And because everything on the outside is filled, you do need to go to the center and place those as pairs. And that's how we get those dots on the central atom, because that's how they should be placed. Now, if we look at this, we have now put 18 electrons. Oxygen's on the left, 2, 4, 6, 8. One on the right is identical, it's the same. But our sulfur in the middle has only 6 electrons. Single bond to the left, single bond to the right, and the 2 dots is 6 electrons. So here again, we need to make a double bond. You could choose either oxygen to do that. So remember that when we make a double bond, we're going to take a pair of electrons. So I'm going to take these guys right here, and we're going to bring them in to make that double bond. And when I do that, I erase the sulfur. We'll put them back, and we will get our double bond right here. This now gives us our 2, 4, 6, 8 electrons for the oxygen on the left. Oxygen on the right didn't change, still has 8. And our sulfur, 2, 4, 6 electrons for all the bonds, and 2 electrons as dots gives us 8. It is happy. This is also one we could draw a resin structure for. We could have double bonded the right-hand side. Would have been perfectly fine as well. Would have looked something like this. Question on those guys. Again, you don't have to draw them both. You could just draw one. You cannot do the double bonded oxygens because technically you do need to have the dots on the top. So hopefully that's what you're asking. You should have the dots on top. So for our class, this is really the right structure here for the SO2. And again, you don't want to kind of double bond out of the gate or anything like that. So you want to kind of minimize those double bonds for some other reasons outside of this class. You don't want to really double bond or triple bond up really oftentimes a lot. A lot of times it will not give you necessarily the better structure. Other questions on that there? All right. I think you got one more there. I had carbonate. So why don't you do carbonate? And there was a request for phosphate, so do them both. Okay, let's see how we're doing here. So carbon, you do usually put the brackets around anything that's an ion. So when you finish the picture, you do want to make sure you put the brackets. That's usually a very common way to draw Lewis structures. So carbon is group number 4. So it's got 4. It's got 3 oxygens, each group 6. -2 going to mean we're adding 2 to our total. That's 18, 20, 24 valence electrons here. We're going to go carbon in the middle. It's the least electronegative. Oxygens on each side. We're going to do a 1, 2, and 3 bonds. And that is 2, 4, 6 electrons. Leaves us 18 to go. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, we have now placed all of our electrons, and much like the nitrate example earlier, we are short in the middle here. Our carbon has only 6 electrons. All the oxygens have 8 electrons, so they're fine. So again, in this case, you could double bond at any of the oxygens. I'm going to go the top guy again, so I'm going to get rid of the electrons up on top. I'm going to bring those electrons in to make my double bond. And again, we're going to put a little bracket around it to make it all pretty looking. And a -2. This again gives me still 24 electrons. Oxygen on top has 8 electrons around it. Oxygen on the left and right also has 8 electrons. And our carbon now has 8 electrons around it. And again, you could draw 3 different structures if you want, but 1 is sufficient. And that would be the correct structure for carbonate. Any questions on that particular one there? Coming to our phosphate here, phosphorus is group 5 there. There's 4 oxygens in this case, each at group 6. And in this case, we do have a -3 charge, which means we do want to add 3 to it. That is 24, 29, 32 valence electrons. Again, phosphorus going to be in the middle. Oxygen going to be all the way around. Going to do 1, 2, 3, 4 bonds. That is 8 electrons that have been used. That leaves me a lot. There's that 24 if my math is right there. And we're going to put those in pairs on the outside. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. I have now placed all 32 electrons. Every oxygen is the same. They all have 2, 4, 6, 8. The phosphorus has 2, 4, 6, 8. It is good to go. We'll put a little bracket around that guy there, and -3. Question on how to draw Lewis structures. If you follow these steps, you will end up with a good picture. If you take each of the parts individually and try to figure out how everybody comes together, not going to end good for you probably. Yes. So I would definitely follow these steps. You want to think about the electrons as that is the total number of electrons for everybody to share, not like nitrogen started with 5, he needs 3 more, or this guy started with 6, he needs 2 more. You will usually, in my experience, end up with not the greatest picture there. So just follow these steps and it should lead you to a pretty good picture. Any questions on that there? Okay. So we're going to come back to that. I think we sort of talked about that. We'll come back to the exceptions. What I like to talk about is geometry next. We do. You should bracket anything with a charge. So anything that's an ion, you want to put brackets around it and the charge top right. So like we did with the NH4, we put the little brackets and the plus on top. We'll come back to all the stuff we went over there in a second here. But let's talk about molecular geometry. And molecular geometry is sort of the structure or the 3-dimensional structure of the molecule with all the bonds that are present and all the electrons that are present. And you can make a pretty good sort of guess in terms of geometry based on drawing a Lewis structure correctly. and how many electrons there are on the central atom and how many bonds there are. So that's kind of the two important things, bonds and electrons. And it's really always the central atom when you're doing geometry. And the idea here is based on the number of electrons that are there, the type of electrons that are present, we may get some different geometries. Electrons ultimately are negatively charged, which means they really don't want to be near each other, but they have to be near each other in bonds and when bonds happen. So depending on whether they're bonding electrons or non-bonding electrons, they do try to get away as far as possible. And what ends up happening is they do end up with some different geometries. And this whole approach of what is referred to as sort of geometry is what is sometimes referred to as VSEPR. And it stands for valence shell electron pair repulsion model, hence why they abbreviate it. But the idea here is, as I just mentioned, there are electrons near electrons. They don't really want to be near each other, so they're going to try to move as much as they can. And what's going to happen is the molecule itself, as their bonds and stuff move, the overall shape of it will move as well. So there's really two types of categories. There's one where we draw the Lewis structure and you have no non-bonding electrons on the center atom. So if you draw it, no dots on the center atom, that's one type of category. And there's ones where you draw the Lewis structure and you have those non-bonding electrons on the central atom, which are the dots. And that also is another type of situation that occurs. The most important thing for geometry is right here. If you have a double bond or a triple bond, if you have one of those guys in your picture, that counts as only one electron pair and one bond. So when you're doing geometry, if you see a double bond or a triple bond in your picture, counts as one electron pair and one bond for the purposes of counting. And that's the most important thing here when you're doing geometry for us. We're going to talk about two different types of names. We're going to talk about the electron pair geometry name and the molecular geometry name, or that is sometimes referred to as the shape. So there's two types of names. One's electron pair geometry, describes how the electrons are arranged around the central atom. And one is the molecular geometry, or shape, the overall three-dimensional shape of the entire molecule. Sometimes those names are the same, and sometimes those names are different. So let us start going here with the simplest one you could have, and that is when you have only two atoms involved, a diatomic molecule. Any diatomic molecule that you have, H2, F2 we've seen, HF we've seen, HBr we've seen, any of these two atoms only. The only way you can arrange two atoms is a straight line, so the geometry is always linear. So that's a pretty easy one. If you got two atoms and that's it in the molecule, and you want to know what the geometry is, it's always going to be linear. There's no doubt about it because there's no central atom. So you got two things connected through a straight line, and that's the pretty easy one. So if it's the same one, different one, atoms or elements, doesn't matter. Double bonds doesn't matter. Triple bonds doesn't matter. Geometry will always be linear if all you got is two going on. Now, if everything was like that, that would be great, but of course it's not. So when we get into guys that have three or more atoms, we do need to look at two things. We need to look at the central atom, the guy in the middle, how many electron pairs it has, and how many bonds. So that's the simplest way to do it. So let's talk about those guys. Let's take a look at the first example. This is beryllium chloride. And beryllium chloride is an exception to the octet rule, but what we want to do here is look at the central atom, and it has one electron pair, two electron pairs. It also has one bond and two bonds. So something that you draw that has two electron pairs and two bonds, the electron pair name, or geometry, is also known as linear. The molecular geometry, or shape, is oddly also known as linear. It is 180 degrees apart from each other. So those two bonding electron pairs decide, I'm going this way. I don't really want to be around you. I'm going this way. And they end up separating each other at 180 degrees. And again, the molecular geometry name is linear. So this is what you want to look for. Central atom, if it has two electron pairs and two bonds, geometry is linear. It's the best way to do it. Most people can't visualize 3 dimensions in their head, myself included. Best way to do this is to memorize bonds, electron pairs, and name. That's the best way to kind of do it there. So the next example that we would have is a central atom where three things are actually attached. And here, if we look at our boron, also an exception here, it has 1 electron pair, 2 electron pairs, 3 electron pairs. Again, the central atom is always the important one. So this has got 3 electron pairs. Also has 1, 2, and 3 bonds. Something with 3 electron pairs, the electron pair name is trigonal planar, also sometimes called triangular. The molecular geometry name, or the shape of it, again, these are 2 different names, is also going to be trigonal planar in this case. That is because these 3 guys get as far away as they can, and that's basically 120 degrees. It is called triangular because if you draw it, it makes like a triangle, yes? So it kind of makes a equilateral triangle going on there, and 3 electron pairs, 3 bonds, molecular geometry name is trigonal planar or triangular. And it is as simple as this: count electron pairs, count bonds. That's definitely what you want to do. For us, you probably don't have to worry too much about bond angles. I'm probably not going to ask you that. And honestly, for lecture, molecular geometry name, the guy on the right, top right, is probably the name you need to worry about. I know in the lab, they talk about the electron pair name on the left. So but for us, the guy on the right, molecular geometry name, is really what you need to know. And I'm probably not going to ask you about bond angles, so you probably don't have to worry too much about that as well. So let's take a look at the next geometry, which is 4 electron pairs and 4 bonds. So if we count the center atom, which again is the important guy, 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs, also has 4 bonds. The electron pair geometry is tetrahedral. The molecular geometry, or shape, is also tetrahedral. And that is 109.5. Again, they have 4 bonds, so the best they could do is kind of get 109 away from each other. Kind of makes a triangle on the appearance of it and almost like a pyramid on the bottom. And again, 4 electron pairs, 4 bonds. Tetrahedral is what you're looking for there. All these names, the electron pair name and the molecular name, up until this point have been the same name. So these guys have been in the same name. And if you look back at all the Lewis structures that you drew, when you looked at the center atom, the guy in the middle, there was no dots or no non-bonding electrons. So whenever you draw a Lewis structure where there are no non-bonding electrons on the central atom, the electron pair geometry name and the molecular geometry name will be the same. So they'll be exactly the same. They will not have different names. It is only when we get non-bonding electrons involved that the names really do change. And that's because we now have non-bonding electrons near bonding electrons. And those guys really don't want to be near each other at all. And that's because of this. Basically, this is the repulsion that basically occurs when we have lone pairs near lone pairs or non-bonding near non-bonding electrons. That is the worst situation. They want to get as far away as possible. When we have non-bonding electron dots near lines, that's okay. The best situation is lines and lines, so bonding electrons near bonding electrons. But when we start to introduce those non-bonding electrons on the central atom, that is where things really start to move away from each other. And what it affects is the molecular geometry name. And to answer your question, yes, NH4 would be tetrahedral because it has 4 electron pairs and 4 bonds as well. Yeah, so it will be tetrahedral as the name of it. So when we look at something that has non-bonding electrons, the name that really changed is the molecular geometry name, not the electron pair name. So the electron pair name stays the same. This one changes when there are dots on the central atom because there are these non-bonding electrons present. So an example that would be like SO2 that we drew earlier. And we drew SO2, a reminder, it looks something like this. I'll just draw the central guy since he's important. When we count this guy, it has 1 electron pair, 2 electron pairs. Our double bond counts as only 1 electron pair. So this guy has 3 electron pairs in this case. It has 1 bond here. Again, double bond counts as 1 bond and 1 electron pair and 1 bond here. It has 2 bonds in this case. Something with 3 electron pairs in terms of the electron pair name is still going to be trigonal planar. But because we now have non-bonding electrons near bonding electrons, the molecular geometry name actually changes because and again, we do get a change in the name because of these non-bonding electrons that are present. Question on that. So 3 electron pairs, but only 2 bonds. Angular would be the molecular geometry name because of those non-bonding electrons that are present. All right, I probably should stop since somebody got to get to the lab. So we will stop there. We have 2 more geometries, just really quick. The exam will be moved to not next Wednesday, but the following Wednesday. And we will finish this up on Monday for sure. We will get into chapter 4. And starting today in discussion, those people that have discussion, we're going to start lecturing on some other material to try to get us back on track from the holiday. And that will also help you out for lab next week as well. So the exam will be moved from not this coming Wednesday, but 2 weeks from today, I think. And it will cover chapters at least 1 through 3, probably 4 as well. All right, if you didn't put here, make sure you get the lab. And I'll see everybody in a couple minutes in discussion. And we will start lecturing, I think, with the notes that are up there, maybe on some stuff in chapter 5. I believe the discussion link's up there. I'll double check right now. So if it's not, it should be up there for Wednesday discussion. All right, I'll see everybody in a couple minutes for discussion. If you're out for the weekend, have a nice weekend.